Hello, welcome to Basics of Finite Element Analysis. This is the second week of this course, and we will continue our journey, and what we will be doing this week is primarily get familiar with several mathematical concepts on which the whole finite element theory has been constructed upon. And specifically in today's lecture, we will help you understand several important terminologies as they relate, and they are frequently used in finite element analysis methodology. So, that is what we will discuss: key concepts and terminologies. So, the first term is what is a dependent variable and independent variable. Okay. So, let us say we have a differential equation d over dx, a du over dx equals, let us say, q of x. Okay. So, this is a partial differential equation of second order. A could be a function of x. So, that is why it has been kept inside the parenthesis, otherwise it could have walked out. Now, here x is the position, and u is a function of x. So, u depends on x. X does not depend on u is, x is independent, does not matter what the value of u is, x is a coordinate in space. So, that is why, so x is independent variable and u is dependent variable. It is dependent on x in this case. For 2D problems, for instance, if I have a relation for temperature, temperature is dependent on two independent variables, x and y. If I have a plate which is subjected to some external forces, in that case there may be three displacements at any given point, u, v and w, and each of these guys, u, v and w, they depend on two independent variables, x and y. If it is a dynamic problem, each of these values variables, u, v and w, which are dependent variables, they depend on three independent variables, x, y and time, x, y and time. So, that is what is about dependent and independent variable. The second term is domain. So, till so far we have discussed and used domain, and I have said that from a practical standpoint it is the region in which we are interested to find the solution of a problem, right. From a mathematical standpoint, the definition is a little much more rigorous. So, what is domain? It is a collection of points. That is the first thing, but then it is not just any arbitrary collection, such that any point P is said to be in domain if all points around P which are sufficiently close to P are in the domain. Okay. This is what it says. So, what does that mean? Suppose this is, so there are lots of points, infinite points, and what it says is that a point, so here we are defining domain in a roundabout way. So, we say that it is a collection of points. Now, there could be a point here also, there could be a point here also, there could be a point here also, and there could be a point here also. Okay. So, let us number these P1, P2, P3 and P4. So, what does it say? That a point is in the domain if all the points which are sufficiently close to the domain are in the domain. So, when we look at point P1, all the points which are very close to P1 are in the domain. So, point P1 is said to be in a domain. So, similarly, we find out what all points lie in the domain, and that collection of points is called a domain. Now, you go to P4, which is very close to the boundary of the domain, but still as long as it is not in the boundary, all the points around it which are sufficiently close, they are still in the domain. So, point P4 is also in the domain. Now, you look at point P3. Here there are some points around P3 which are in the domain and some points which are not in the domain. So, we do not say that point P3 is in the domain, and for similar reason point P2 is also not in the domain. Okay. So, what it directly implies is that points on the boundary are not in domain. Okay. Another, so this is another, it could be domain and it could have an internal boundary. So, it could have an internal boundary and an external boundary. So, then points which are here, let us say this point P1, this is not in the domain, point P2, this is not in the domain, but point P3, it is in the domain. In a lot of our further discussions, we will designate domain by this symbol omega, and this is also a fairly standard symbol used to denote domain in a lot of technical literature. If I say that my domain is an element, lot of times we will say that omega subscript E, which means this is the domain of an element. Third concept, convex and simply connected domain. So, what does, so a domain could be convex and simply connected, or it may not be convex and simply connected domain. So, what is a domain which is convex as well as simply connected? It is, this is how we figure out if P1 and P2, if P1 and P2 are any points in a domain and if line P1, P2 lies entirely in domain, then domain is convex and simply connected. Okay. What does that mean? Consider this domain. This is a rectangular domain. Now, you take any 2 points P1. This statement has to be true for all sets of all the points in the domain. So, you take any 2 points and if you join them through a line, that line will always remain in the domain. Okay. So, this is an example of simply connected as well as convex domain. Now, you take another domain. Okay. If I take this point and I take this point and I draw this line is not is totally in the domain. So, this is not convex and simply connected. Okay. Another example, a circle is a simply connected domain, but if I make a small circle within a circle, okay, then it has 2 boundaries, boundary 1 and boundary 2, and then I can have 2 points, this is point 1, this is point 2 in the domain, and the line which connects them does not lie entirely in the domain. So, again this is the example of a not convex and not simply connected system. Okay. The reason why they use the term convex is that convex, you see, you know what is convex lens? So, it tries to focus all the rays to a point, it tries, and then, so that is a very good, that is a feature of lot of, for instance, you have a regular hexagon, this is simply connected domain, you have an octagon, this will be also simply connected, you can have a circle, you can have a triangle. But the moment you have some non-convex, see here all the angles are less than 180 degrees, but if you have like this angle is not less than 180 degrees, and because of this you cannot say that this will be simply connected because of one. Okay. So, this is what a simply connected convex domain means, and I should have mentioned that we always define symbolize boundary as this gamma. Okay. So, in this case, for this example, there are 2 boundaries, gamma 1 and gamma 2. So, whenever we try to integrate a function on the boundary of a domain, it is not that we just only worry about the outside boundary, we have to integrate it on all the boundaries, whether they are internal boundaries or external boundaries, it is important to understand. The next term is function of class M. There could be a function, it can have a class 1, it could have a class 0, it could have class 2. M is a number, integer. And it is designated as Cm. C is class, M is the integer. So, a function is of class M in a particular region, not region, domain. Okay. What does this mean? A function is of class M in a domain, it has to satisfy 2 requirements. It should exist in domain at all points. So, when it exists in domain at all points, does it require that it has to be on the boundaries? No, because the points for the boundary are not necessarily not in the domain. Okay. And the second thing is all of its partial derivatives up to mth order should exist and should be continuous in domain this thing. Okay. So, for instance, so this domain could be one dimensional, two dimensional, three dimensional, it does not matter, right. For instance, let us say my domain is a set of points from 0 to 10, x. Okay. So, what does this mean? My domain is on the x axis, this is 0, this is 10. Oh, I am sorry. Yeah. Yes, you are right. So, this is my domain. And then I have a function, let us say, and let us say it is equal to sin of x. So, then I see that sin of x is a well defined, it exists at all the points between 0 and 10. So, this condition is true, and then I also see that df over dx exists for all the points in this domain 0 to 10, and all of its derivatives actually exist. I can keep on differentiating it. So, this is a class infinity, right. It is infinitely differentiable, but if I have another function f of x, and let us say it is equal to 3x square, right, then I have the first derivative exists, second derivative exists, but third derivative and onwards does not exist. So, this is a C2 function in this domain. Okay. Understood? Now, if you have a 2D domain, let us say you have some complicated shape, you have a 2D domain and there is a function and let us say there is a function f of x and y equals 3x square y cube. Then the way we figure out the class is that all, so does del f over del x and del f over del y exist? So, the answer is yes. So, it is certainly m is 1 or higher, and you go on figuring out the partial derivatives, right. So, then you take the second order derivatives, and if they exist, then it will be C2 if higher ones do not exist. So, del 2f over del x square and del 2f over del y square, they also exist for this function, and but this guy does not exist, and higher terms, right. So, this is C2. Okay. So, now domains could be one dimensional in nature, two dimensional in nature and three dimensional in nature. Actually, they could be of higher dimensions also, but in context of this course I think we will be here. And then their boundaries. So, a domain could be like this is one example of a domain, these are the endpoints. Another example of a domain, now this domain is not simply connected, right. So, this is example 1, this is example 2, because there is a point here and there is a point in this one, and if I connect them, all the intermediate points between these 2 points do not lie on the line. So, this is a 1D domain simply connected, this is a 1D domain not simply connected, right. In this case, the boundaries are just endpoints. A 2D domain is a basically some surface. It could be a flat surface or it could be a curved surface also. It could be a curved surface also. So, here it is a line, closed line, right. And here this could be a 3D object and here it is a surface. Finally, we will talk about what are boundary value problems, initial value problems and eigenvalue problems. So, we will explain what are these. So, these are the 3 types of problems we will solve in our in our course. Okay. So, I will explain this by an example. So, let us say my differential equation is this minus d over dx a du over dx is equal to f. So, here u is the dependent variable and it depends only on x, which is the independent variable, and this is valid between, let us say this differential equation, governing equation is valid in this region and the value of u0 is equal to some constant b naught and the value of a times du over dx at x is equal to 1 equals g naught. Okay. So, what you see is that this is a governing differential equation and I have prescribed the primary value variables and some functions of its derivatives at the boundary. What are the boundaries? 0 and 1. So, I have prescribed, either I prescribe the primary variable or the dependent variable at the boundaries. So, this is a boundary value problem. Okay. This is the example of a boundary value problem. The second category of problems are, again I will explain through example. So, this is my second category is initial value problem. So, in the first case we are prescribing primary variables or their dependents or that is their derivatives and stuff like that at the boundaries. In the initial value problem, consider this equation. So, here u is a function of time. Okay. So, this could also be a function of time and u is a function of time. Okay. This is like your equation mx double dot plus kx is equal to c, it is something like that. And this equation works for different values of time and the value of u at time t is equal to 0 is u naught and the value of its derivative v naught. Okay. So, this is the initial value problem. So, in the first case I was prescribing the values at the boundaries, physical boundaries, they are physical boundaries. Here I am prescribing the value of primary variable and its functions not at only one boundary, which is t is equal to 0. There is no t is equal to something else other boundary, right. So, I am prescribing u0 and its derivative at the beginning of time, which is t is equal to 0. So, that is why it is called initial value problem, because I am prescribing conditions which exist initially, not sometime later. Okay. So, that is the initial value problem. And then I can have problems which are both boundary value as well as initial value. So, as you are developing solutions, FEA solutions, you have to look what is the type of problem. Okay. So, here I will again write down an equation. So, here u not only depends on x and it not only depends on time alone, but it depends on both. So, u is a function of x as well as time. So, here we have two independent variables and one dependent variable, and this equation I say that it is valid between x is equal to 0 and 1 and also between time more than 0 and some time t naught. And here I am saying that okay, value of u at all times at x is equal to 0 is b0 of t, some function of time, and b0 is known. Then value of a times del u over del x at t is equal to 1, excuse me, at x equals 1 is g naught of t, and finally u of x 0 is u naught of x. So, all these b0, g0 and u0, they are all known functions. B naught and g naught are known functions of time and u naught is a known function of x. Okay. So, what are we specifying here? We are specifying the conditions at the boundary. This is my x axis. So, this is x is equal to 0, this is x is equal to 1. So, I am specifying all throughout the time the value of u at x is equal to 0, this is condition 1, this is condition 2. Okay. So, I am specifying the value of u for all values of time at x is equal to 0 and x is equal to 1. So, I am specifying stuff on both the boundaries. So, in that because of that it is a boundary condition, and I am also specifying at all the points at time t is equal to 0. So, this is the condition 3, and that is why it is a boundary and an initial value problem. So, I am stating what the system looks like initially and how it behaves at the ends at all times. Okay. Another thing, there are sometimes people say that this is a homogeneous boundary condition and this is a non-homogeneous boundary condition. So, if B0 was 0, then we would have said that this particular condition is homogeneous boundary condition. If this u0 of x was 0, then it would be a homogeneous boundary condition. If it is non-zero, then it is a non-homogeneous boundary condition. So, this is the last another thing, and last thing we will talk about eigenvalue problem, EVP. So, we have talked about BVP, IVP, BV plus IVP, and this is the last one is eigenvalue problem. So, in eigenvalue problems we solve homogeneous differential equations. See, earlier we talked about homogeneous boundary conditions, here we solved homogeneous differential equations. So, what is a homogeneous differential equation? For instance, d over dx a du over dx minus lambda u is equal to 0. So, first let us look at this equation. This is a non-homogeneous equation. Why? Because the right side of the equation Okay, so first thing is that on the left side we have put all things related to u, which is the dependent variable. On the right side there is no u term. So the non-u term is fxt, it is a forcing function, okay, it is a forcing function, and here forcing function is non-zero. Now we look at this equation. Here all terms on the left are again in u or their derivatives, but on the right side the forcing function is 0. So this is a homogeneous differential equation because f or forcing function is 0. So it is a homogeneous differential equation, and in this case we solve this equation and we solve it to find the values of lambda. Okay. First we solve the values for lambda, so this is 1 and then 1, so we will get several values of lambda. Okay. We may get several values of lambda, and then for each value of lambda we find value of not value of u, we find, okay. So this is, these are numbers, and for each value of lambda we find u of lambda, and these are functions. Okay. These numbers are called eigenvalues, and eigenvalues is one single word, it is not two words, it is one single word, and these are known as eigenfunctions. Eigenfunction is also one single word. So here I have just written one particular type of homogeneous differential equation, but any homogeneous differential equation, it does not have to stick to this form, is where we find some numbers like this lambda, and these numbers are called eigenvalues, and then associated with each of these numbers is a u function, and these functions are known as eigenfunctions. Okay. And the last point I wanted to mention is that in German this term called eigen, it relates to something relates to identity. It may not be the exact translation, it relates to identity. So here there is no external force. Okay. So the system, the behavior of the system is purely dependent on the internal characteristics of the system. It is purely dependent on the internal characteristics of the system. It is, so these lambdas are basically the identity. If there is nothing external, so howsoever the system is going to behave will be purely driven from the internals of the system. So that is why this idea of identity of the system is related to this thing called eigen. Okay. So that is there. So this closes our today's lecture, and we will continue this discussion tomorrow. Thank you very much. Bye.